over to the United States, and then the last I think around 30 years, 27 years actually I'm over there. I did my PhD, and then I'm right now a faculty. So, today what we would be talking about, first of all I wanted my lecture to be more interactive, but I think because of shortness of time I do not know how interactive it is. First is I wanted to know more about you before, that is normally I do when I teach my class. I wanted to, I ask my students to give like a 1-minute introduction about themselves, but I think because of shortness of time and it is a large class I am kind of skipping that. But I just wanted to show of hands, because we are showing 2 lectures today. One is introduction to nanotechnology and the introduction to nano biotechnology. Basically some part of the lectures are the same if you even have looked at in the PDF. The nano biotechnology basically tells the application of nanotechnology in the field of biology, which is the focus of this seminar. But I wanted to give you introduction of nanotechnology. So, how many of you have had a course or know what nanotechnology is other than just the name? Okay, so I see about maybe roughly counting about like 40 yeah 30% I think. So, this lecture, as you can see, it's the purpose of this lecture is, oops sorry, how do you come back this one? Okay. So, the purpose of this seminar is, this is a non mathematical survey to motivate the interest and heighten the awareness in nanotechnology, intended for all students. I was involved, this one is it? Yes, it's fine. This is a part which we put together. I was involved in the state of Connecticut. We developed from the Department of Higher Education. It was a nanotechnology minor program for undergraduates. So, there was, again, this program has not been offered yet, but the courses and all have been developed. So, this was the first course. It was a 1 semester course, and this is kind of taken as a summary of whatever we were supposed to teach. The focus is why, again, do you know from when we are using the word nanotechnology?
Lecture series in California. They have given a lecture in California in 1959.
Yes, he first said what was the his famous quote, which says there is a lot of room at the bottom. So, it is basically we would just tell why nanotechnology was important. Then there was time when actually in engineering, microprocessors were there, people were working in the micron scales, and then on the other side in the medical cell, people were working in the micron scales with biological cells. They are all in the micron scale, and how does nanotechnology kind of link them together? That is what I will talk. And also, now why nanotechnology was important, for those who have taken the courses, you would know it changes the physics. What we know so far, any object, if I give it a force, it's Newton's law which dictates how it would move, or if you pass a current through a wire, it is Ohm's law which dictates how it would. But in nanotechnology, these things get a little modified. Why? Because if this thing gets extremely small, if I hit it, I do not know whether I would be able to hit it or not. There is a probability that I might miss it, I might hit it on the top, I might hit it at a corner. So, if I hit it, it might spin, go, it might have different types of motion. So, that is why not only Newtonian mechanics, we would talk a little bit, it talks about already a branch of physics that has been developed to talk about that, quantum mechanics. So, there has to be a part of that also involved there. In Ohm's law, when we switch the circuit on, connect the switch, current flows. Nobody ever worries about is there a shortage of the current unless the battery is running out, but when materials get smaller there are only a few electrons available. So, if you exhaust all the electrons going over there, there will not be any more current. So, that is why there are special effects which generate because of that. The current does not go in a very linear way, it kind of jumps, and so that is one of the other thing that happens. Also the final thing which that makes nanotechnology special is, we will talk about this in a minute, is, or I would not actually what I would do, there are I think about 60 slides over here. So, what I would do is I would go through, you can see what is written over there. I will try to, again depending upon how much you are able to digest the material. Is it okay if I ask you questions? Okay. Again, I do not know your names, normally I do, but maybe I will again there would be a probability I will point it at someone, maybe one of the 3 people, front row, back row will kind of give the answer. So, anyway, it is the one property of nanomaterials which makes it more is, which we will talk about, is the surface properties override the bulk. Normally when you have a material, when we calculate the mass is, how do we calculate the mass of this material? We do the volume times area. So, we assume every molecule, everything over there is inside in the volume, we ignore things which are here on the surface. Okay. But when you make it smaller, what happens is the volume gets smaller and everything goes over on the surface. And from geometry, you know what is the volume of a sphere, formula for volume of a sphere, 3r cubed. Okay. And what is the surface area of a sphere, r squared. So, there is an order difference in the exponent. So, r cubed and r squared. So, that makes the forces kind of vary, because right now when we know Newton's law of gravitation, G F equal to G m1 m2 over r squared. Anyway, my background is in physics, so I kind of try to portray all these the basic elementary equations. So, that is and Coulomb's law, the same thing, q1 q2 over r squared. So, those assumes that the material what we are considering has, most of it is the volume. Now, when you look at the surface, then some other forces come into play, and that plays surface tension, which I think when in the lecture, the first lecture, Professor Chakrabarty, he talked about the surface tension. The surface tension forces come out very significantly, and sometimes that force is a lot stronger than the bulk force. Any one of you who is trying to wear your clothes when you have not totally, after your shower, when you haven't totally dried yourself, you would know, especially if you are wearing something which has a polymer, you would see that whatever you are wearing, it kind of sticks. What makes it stick? It is the surface forces, and the surface forces play a significant, and that is primarily how biological things kind of get attached with. And there are a lot of research going on for making very good glue, how to make it, how you would glue something to a metal. Welding, you can weld metal, but how if the other side is not a metal. For example, I think you are familiar, people are right now working with composite materials. The recent the Boeing airline 787, which the Boeing came out, and a lot of airline companies including Air India bought a lot of them. You know why people are buying Boeing 787? Because of gas mileage. A normal plane, if it flies across the Atlantic, how much fuel it consumes? The Boeing 787 consumes only 60% of that fuel. So, basically you can make 3 trips with the same amount of fuel as you would make with one. And how do they do that? They make it, they don't replace the metal with composites and make the plane is light. Okay. So, that is again they can't weld the materials together. If it is made of composites, you cannot weld it. There are different techniques of going there, but it is basically a type of glue which holds this. And so that is, you might feel a little bit eerie when you are flying on a plane which you think is kind of held by glue, but these glues are really strong. I can tell you just one of my personal experience. Once I was making a flight to New York, when one of the doors of the plane, the back door of the plane was not totally closing, so that they put the latch on, and the flight crew came in with a duct tape and duct taped the tape over there. I was really scared, but it made the entire flight from London to New York with the duct tape still there intact. So, again it increased my confidence on duct tape. So you would know that how much glue can do. Okay. So, it is not, you do not have to weld everything, and what is holding the glue together? Surface tension. Okay. So, that is where nanomaterials come into play, and we would talk about that. Okay. So, let us I will use this one. Again, I think you must have seen this picture long time. It was a cover of Scientific American. Then do you know what this is? It is a silicon atom. It is an atomic force microscope of silicon atom's surface. Okay. So, the main idea of nanotechnology was whatever it was promised, we have not been able to do that, but we have been able to use it as a byproduct of something else. Okay. So, initially Richard Feynman, I think, never envisioned a thing on biology and nanotechnology together, but that is where we have suddenly found the application sticks more. Okay. So, this is the famous quote of Richard Feynman, which kind of there is plenty of room at the bottom, which first gave the idea of nanotechnology. We discussed this before. Again, what is a nanometer? I think all of you know that. It is 100,000 times thinner than a strand of a hair. Again, do you know the orders of magnitude as we go lower? Nano is 10 minus 9, then you have 10 minus 12 and pico, which is occasionally is used. Okay. Then 10 minus 15 femto. What is the dimension of femto? Anything you know in the dimension of femtometer? Nuclei means you are talking about nuclei of a cell or nuclei of an atom? Okay, yes, nuclei of an atom, nucleus of an atom, that is right, 10 minus 15, and 10 minus 18 is known as atto. Okay. Up till there we stop, like on the other side when we go, what is 10 to the power 9 known as? Billion. Okay. So, the positive side is then 10 power 9 is billion, then 10 to the power 12 is trillion. And after that we do not have names of things after that. So this is just to give you an idea where oops, it's gone away. Did I hold it too long? Okay. So again, this is, I think you have seen this picture, the slide again in a lot of the other ones. So I will just skip to get you an idea of the size. Again, we use the word nano technology kind of a little loosely. Anything in the order of 1 micron, and this regime you call it nanotechnology. It is not always like when in the first lecture when we were talking about MEMS, we were using about microelectric. So we were talking about micron size, because we have a control of how to make things in this scale, but to get it into this we are still struggling with our current technology. Again, that is why there we have to look for alternative ways of making up things. We talk. Sorry, I should be doing this. So, again, this is just blowing up what happens. So, if you take your hand, hold your hand like this, this is everything is kind of blown up by factor of 10. So, this is 10 centimeters, then as you go blowing up factor of 10, this is 1 centimeter, 1 millimeter. In 1 millimeter you see that the skin is having creeps, you are seeing parts of the skin. 100 microns, 10 microns is when we see the size of blood cells, 1 micron when you are actually looking inside the blood cells, inside the cells, 100 nanometers, 10 nanometers we are looking at DNA, and when we go into 1 nanometer we are looking at the individual components of the DNA. So, that is why when we look in nano, what I will be talking when we talk about nano biotechnology, there is a field in biology known as molecular biology and genetics, that is which deals with these stuff. So, that is where nanotechnology overlaps, and that is where we would be talking about nano biotechnology. It has nano biotechnology has given you new instruments, so that you could probe these things a lot better. So, the way I will actually, it is a part of the next lecture. So, I will talk about that. So, what are the common particles which are of nanometer scale? The human hair, we talked about that before. Smoke particle, again this depends upon what type of smoke particle you are talking about. Smoke you can generate from different sources. This is 1000 nanometer smoke particle, I think it comes out from a coal power plant. Okay. So, if you have if the smoke that is coming out from your car exhaust, particle size is lot smaller than this. Okay. So, again virus is in the order of 3 to 50 nanometer, DNA, a nucleotide, and hydrogen atoms or any atom for that size is lower than that of 1 nanometer. Sorry, every time I am used to pressing that, so I am going. Again this text tells you how much we could store the view of matter in the nanoscale, I think. So, when we have you seen this movie? This was a movie which called, they had a character known as Mini-Me. This is a person kind of made smaller, and so how much smaller you can get, and when you can go in the smaller scale, these are the things that these are the size and these scale factors what you can observe. What I wrote over there, it is kind of the diagrams of that. This is the hydrogen atoms, this is the virus particles. We could do. Steven Spielberg had a very famous movie, if you have chance you can look at it, it is known as Inner Space. In the inner space, they tell that some person has been made so small that the person is in the size of a white blood cell. So, the person has gone inside the blood, and they have excellent video of showing how the person, when it is going through the blood vessels to the heart, to the different organs of the body, is swimming, and how they see, and finally the person comes out through the retina of the eye and has a view. So, how you would that is how the person knows how they are seeing the external world. But anyways, when Steven Spielberg made that movie, nanotechnology was not there, but nowadays we can actually monitor things in that scale. So, as matter is what you can see is when we make things smaller and smaller, we go into the nanoscale dimensions, there are changes in properties, and the main change in properties that comes in is they are all nano dimensions, they are practically all surface. So, when you take a nanometer, if you calculate the number of molecules which are present in the bulk, the ratio of the number of molecules, how do you know where the surface property dominates? You have to assume how many molecules are there, and if you find the ratio of the molecules, how many molecules are there in the volume versus how many molecules are there in the surface. For nanomaterials, it is more than 50% of the molecules are there on the surface. For this material, how many molecules would be there on the surface? It is less than 1%, most of them is inside. So, that is a way to kind of know when the nanomaterials will come. So, that is what. So, this allows for an increase in chemical interactions. The atomic and electronic structure of the nanostructures change, and so does the optical electrical behavior of matter. So, that is what makes nanomaterials interesting, because if you can go in that level and study, then some things what we already know are being changed. For instance, what do we know of gold? What are some of the properties why gold is known for? It has very good electrical properties. Anything else? What about reactivity? Gold is inert. That is the reason why we use it for ornaments, because otherwise even silver changes color, but gold does not. Okay. So, that is why, but when you go into nanoscale gold, it is one of the most extremely reactive particles. It is actually used as a catalyst for a lot of reactions. It is used as a catalyst, and it's extremely. Also the color. What is the color of gold? Is golden color, we call it golden. It's kind of a little brownish, means it has a color which is named for it. But what about nano gold? Nano gold, depending on the size, you can change the color. Actually, you could do a very simple experiment where you could make gold particles, and then as the particle changes in size, the color changes. It can change from blue to red depending on the size of the particles. People who used to paint knew this. In fact, that is how artists used to make colors on their paintings. Even if you go to, I am sure in Ajanta, Ellora, if you go and have you look in the paintings, artists actually use nanoparticles to paint. They did not know that they were making nanoparticles, but when you make the size small, the color changes. Why does it change? Why do you see color? It is what gets absorbed and what gets reflected back. But again, if the size gets smaller, the amount of thing that gets reflected back, you do not get that much reflected back. So, there are other, so that is why the color might be. So, normally anything which you make small, what color would it look like? Black, because it is not reflecting as much light as it would be possible. But then the other effect, we will talk about that, quantum effects come in, that is when the electrons jump from one level to the other, they actually are luminescing, they are producing their light, and that overlaps, and that is why. Anybody who has worked with silicon wafer would know that the thickness of oxide layer on the silicon wafer we can tell by looking at the color. If it is bluish, if it is bluish green, it is again the same property, nanomaterials that will. So, whatever we know about the periodic table, things have changed. There are two English adjectives, one is strong and one is light. When we use, they do not have anything in common, but whenever we use for materials, they normally come in together. When we look at a material which is strong, not they do not come in together, I mean strong and heavy, they are all, because the materials what we know are steel, which we use for construction, that is strong and as well as it is heavy. So, but nanomaterials you can differentiate them. A material which is strong need not be heavy, it could be light, we would talk about something known as carbon nanotubes, which at the same time can be strong and light. I said Boeing used these materials to make their Boeing 787. So, the Boeing 787 is actually stronger than the other airplanes, but it is very light. There is work going on where we have in MIT, where they have designed clothes which can be bulletproof. So, normally if you see a bulletproof vest is this thick, people wear it, this deflects the bullet out, it has to be strong. But if you have materials which can be strong and light, they can make it almost the same as the clothes. And in fact, they used it in some of the troops experimental stage when the troops went to Iraq, they were wearing that type of vest. Okay. So, whatever we know, electrical properties, other properties, they change. We can make copper into an insulator, we can make an insulator material into a conductor by making them into nano. So, how are we doing on time? So, there is only 1 hour left, is it? Okay. So, this is the carbon nanotube material which we talked about. I think there is more about this material. My entire research was on this material, carbon nanotubes, and we would talk more about. Anybody know about carbon nanotubes? Yes, can you?
It's a 2D array of the graphene layer that is folded in a cylindrical form, and the ends are closed.
Okay, end could be closed or could be bottom or open.
Mostly they are closed.
It is a graphite sheet which is known as the graphene. They are kind of formed into a cylindrical form. They have a hole like this. They, if you look at the carbon nanotubes, this is how they look at. There is a hole here at the center, and then there are walls on the side. Again, if you look at it, this size is 10 nanometers. So, each of these, the sizes are about a few nanometers, 3 nanometers, 4 nanometers. So, why these are important? Because these materials are the if you look at it, if you calculate their Young's modulus. Young's modulus is the way you find out how strong they are. Their Young's modulus is actually 1,000 times more than that of steel, but they are extremely light. Why they are light? Because first of all, about 80% of them is filled with air, because inside this is hollow. So, the only material is on the outside. So, that is why they could be extremely strong and light. In fact, there was an article earlier in Scientific American. They said a space elevator. You know, they are sending out the satellites up in the sky, and the satellites, what happens to the satellites is once they stop working or you have to repair them, you have to send, because if it stops working, you do not want them to be hanging out in the space there, because then they are become like a projectile. They would be hitting other things in space, and then eventually they would be coming crashing down if something happens. So, you need to, and currently I think ISRO did one rocket which went up, and there are a lot of private companies which are trying to have cheap rockets that can go up in space. And so, one plan of that they wanted to make was making a space elevator, something like an elevator which would be taking you up in space. You know the height of the tallest building in the world? Yeah, Burj Dubai. It is slightly more than 1 kilometer. Okay. Mount Everest is 8 kilometers or 9 kilometers, and so just to give you the scale of things. So, the space elevator, you can think how long it would be. It at least has to be 20 in the actually the stratosphere is 20 kilometers. So, it has to be 20 kilometers. Now, suppose you can build something which is gone 20 kilometers. How you will build it is I do not know, but suppose you can build one thing, you can calculate and find out what would be the weight of that material. 20 kilometers, there is no rock, there is nothing on the soil of the earth which would be able to hold it. So, even if you are about to build something 20 kilometers high, it is going to sink and you would not be able to. So, there is a limit to how you can build with our standard materials. So, the only way you could build it is if you someday if you use materials like this. Oops, again press the wrong one. If you make something like this. So, that is why you would be so you could this could be strong as well as they are light, but right now the main problem of these materials is they are not very long. Each nanotube, the one which I looked at over here, how long they can be? They can be maybe 100 microns. 100 microns is even less than 1 millimeter. 1 millimeter is if you use a scale, the smallest mark of that is 1 millimeter. So, it is even smaller than 1 millimeter, that is the longest nanotube you can make. And when you join 2 nanotubes, there are methods you can join 2 nanotubes, but there you lose most of their strength over there. So, that is the place they would be not as strong as before. So, that is one of the problems of right now making net. I was involved in a project by the US Department of Defense where they are trying to make a kilometer long nanotube. Okay. So, one nanotube which would be 1 kilometer long. The project did not have a very successful ending, but still people are working on it. The whole idea is to make the long nanotube, so you can use it for structural purposes. You could also use it. Nanotubes also have unique properties which we would as you look at it you would see this is we talk about mechanical properties. Then about electrical properties, nanotubes have very interesting electrical properties. Anybody knows about that? Nanotubes, it can be both a conductor as well as a semiconductor. There is no material which in its intrinsic form can have both electrical properties. So, what decides whether it is a conductor or a semiconductor? It is the diameter. It is actually, if you look at it, it is how the sheet is kind of wound, that kind of they have a property known as chirality which decides whether it is a semiconductor or a. So, that was the project which I was involved in. They were trying to make not only 1 kilometer long, but they were trying to make an entire circuit on just one nanotube, because they could make a transistor, you could make a conductor wire, you can make everything depending on, because the same material can be semiconductor and metal as well. Okay. So, that is a very important property is you can, and the other part which makes nanotube very important even for biological purposes is the surface properties, as we said, was that it dominates. So, surface property dominates is if you change the surface slightly, its conductivity changes. So, say if you expose the nanotube to oxygen, oxygen comes in, oxygen gets in on the surface of it, its electrical property changes. So, you would be able to know extremely very good oxygen sensor. So, or any other gas materials, whatever that comes in over here exposed to the nanotube surface, it changes. Why? Because how the nanotube conducts is through the surface. It actually, if you look on the surface, it is they what we call as they are conducting through pi bonds. Is if you look on the surface, you have the graphite surface has carbon atoms forming like an hexagon, but then on the surface of it you would be having pi bonds which are like things which are sticking out, and these pi bonds overlap a little bit, and that is how electron conductivity occurs. If any material comes in, what they do is they knock off these pi bonds because they are combining with them, and so that obstructs the path of current, and that is why it is. This is used as a DNA sensor, and I will be talking about that. Is if the DNA comes in, DNA combines over here, there is a change in electrical properties. So, that is why nanotube is used as a sensor. Why? Because it is so small that only one DNA might cause a change, which you would be able to do. All our current measurements, again in our first lecture, that is the only lecture I have heard. I did not hear Professor Das's lecture. So, I am sorry I am not being able to quote what his lectures are, but he told that we want to make our diagnostic with as little blood as possible. Right now we need more blood. Why? Because we can't detect one DNA, one cell, these type of things we cannot, our measurements, we have to do it for a large amount, and so that is why we need large quantity. But with these we can be extremely sensitive. So, parts per billion, parts per trillion, parts per, these are the ways we know. These are currently also used for detecting hydrogen sensors. It is used because hydrogen, as you know, in fuel cells, it is something which is which if it leaks it can cause explosion. So, this is one that has been used. So, that is also talked about, that carbon nanotube. And the last of the, and important, not last, there are a couple of other important properties also. The other important properties which makes carbon nanotube unique is once again going through this hole, it is hollow. So, what does hollow mean? You can actually put things in the in over there, and then if you don't want them, you put it there. If you want them, you can squeeze them out. So, where it is used as? It is drug delivery. Yes, it is one place that is used as, but the other place where it is used more is as a rechargeable, anything you want to make generate energy, rechargeable battery. How batteries work? Batteries work when you have two electrodes and then transfer of electrons. Why does batteries run out? Because this cannot supply any more electrons to run over. Now, when you charge it, you have to put those electrons back, but normally if you put the electrons over on this side, they are lost. So, most of the 80% of that is lost, but here they will not be lost if you can put them inside the holes, and then when you want it, you can squeeze it out. So, that is a very important place where you can use it. You can use it as an extremely filtering mechanism. We saw I said the size of the dust particles is 1000 nanometer, but those are big chunk of dust particles. There are dust particles everywhere. If you are looking for a fabrication facility, you have to make your dust particles extremely small, because one small bit of dust particle falls on top of it, there would be problems. So, how do you make dust particles how do you prevent dust particles very small getting in? You might use this one as a filter. So, you can stop extremely small amount of dust particles from you can use it for. The other place where people were trying to use this was, there was a big fad of using hydrogen as a source. So, that is why they were using. Anyway, these are non-biological applications, so I do not want to spend more time on talking about that, but that is what makes this is. But why haven't then been able to make? The thing is, the nanotubes are, how do you extremely small? It looks fine if you can squeeze it out, but how will you squeeze it? Look at the size of it. Is there anything that can hold it in this size? What do you normally hold it? It is known as a tweezer, or anything that you try to hold things up. Here there is nothing that is available by which you can squeeze it. So, if you put materials in there, they will come out on their free will. You can heat it up and expect some of it to come out, but then there is nothing. So, that would be. So, that is one of the problems. So, everything, as I said, carbon nanotube shows lot of promise, but then if you look back more deep into it, there are limitations. For sensors, biosensors or any other sensors, what is one big limitation is finally how will you make these contacts back onto your regular circuit. Whatever contacts you make, you cannot make contacts of 10 nanometer size. Even lithography, whatever you do, whatever I think Professor Das talked about, you can't make features. Intel right now is working very hard in trying to make those nanometer, those mass to work on it, but still to make contacts of 10 nanometers is not possible. So that is how you make, there is an entire area where people try to work on it. If one that is, can I spend too much time on this one? I gave you examples of nano gold. I told you that gold can turn red, blue, yellow, other colors depending upon their size. This picture basically shows you have gold in different, and they are showing different colors. So 12 nanometer gold particles look red. So you can make them. So silver nanoparticles, you can do exactly this, the same. I'll spend more time in explaining what is something what we call as quantum dots. That has lot of application in the field of biology. Okay. Just a brief description. Anybody knows what a quantum dot is?
So quantum dot is a structure in which the electron is the movement of electron is confined in all the three directions.
Right. So thank you for your I think you have a course on, you have taken a course on nano. So when you make nanomaterials, you can make it them into one dimension, you can make it into two dimension, or you could make it into what we call as 0 dimension. Okay. One dimension is, we talked about carbon nanotube, that is like long, it's only, we are assuming it's on one dimension over here. Two dimensional nanomaterials is we talked about graphene or any sheet which is two dimensional, and 0 dimension nanomaterials are which are like a dot which does not have anything. So quantum dots are not all 0 dimensional nanomaterials, do not make quantum dots. So quantum dots are a special type of those 0 dimensional materials which are primarily made from semiconducting materials. So they have to be either a semiconducting material, cadmium selenide or other because there has to be place as can I know your name please? Rohit, as what Rohit said, it has to do with the electron level in over there. And so what happens to quantum dots is since it is confined particles, is when you shine light on it, they can shine up very brightly what gets reflected out. So a very small dot can produce a very strong piece of light that comes out from it, and that is where it is used as a biological detection. How do people know how many, if you have an infection or something, they want to count how many blood cells you have? They basically put the blood cells and then they put some colorant on top of it, and they look at the change in color, how many cells have green color, how many. But the quantum dots, look at their size are so small, so only a few of them would be bright enough. So you could, so that is one of the big things is right now you would be able to detect one cell or two cells. Right now you cannot detect one or two cells because the light it generates is not enough for you to capture. So that is why with quantum dots you could look for a lot of detection mechanisms which are a lot more sensitive to that. I saw a demonstration of an instrument which was just using with a smartphone. Is there are a lot of people who are allergic to nuts. When you have something with nuts, I am also allergic to nuts, but I am not that severe. Is if you have anything that contains nuts, then you have blisters, and sometimes you can choke. But how do you eat something and know that it does not have nuts? Okay, so you can't question everything. So there is a sensor or detector which is made which can find out whether a material what you are eating has nuts or not, because nuts have a certain chemical. So what that thing does is it uses quantum dots. So whatever you are eating, you take a small drop of it, put it on top of the sensor, and then you can take a picture of that with your phone, and the phone's resolution smartphone's resolution is good enough for you to detect if there is a quantum dot over there. It would shine. If there is a nut, then it would show up over there or not. So, this is a device which is available, you can buy it, it is not there in the lab, it is available. So, that is other places where quantum dots are also being used. Quantum dots, another place where it is being used is people are trying to simulate photosynthesis. So, plants, how do plants take sunlight and convert it into energy? So, people have been able to simulate photosynthesis with quantum dots made out of cadmium selenide. The only downside of cadmium selenide, if anybody has worked with it, you would know that it is extremely poisonous. So, that is why it is not being used in large scale, but cadmium, both cadmium and selenide, if it comes in contact with our blood, it has a lot of toxicological effects. Okay. So, you have to look, this is the cadmium selenide quantum dot nanocrystals, the pictures over here. Okay. Change in properties, the size, I just gave you an example. Opaque substances become transparent, copper, you can make copper in transparent, inert materials becomes catalyst, stable materials turn combustible, solid turns into liquids, insulators becomes conductors, materials. So, these are all the properties, some of the properties which we can change. So, so how nanotechnology stages of where it is being used, or where the nanomaterials, again as we said, every time when we talk about one nanoparticle, one nanomaterial, it is very difficult for us to do, but a part of it is being used, and it is being used primarily as an additive to other materials. For example, the Boeing 787 which I talked about, there the carbon nanotubes are used, but is the whole airplane made out of carbon nanotubes? No, they can't make that much. They are used in certain places where you would use for more strength, and that would be the places where you would be using that. So, that is where we here it talks about how you would be using nanomaterials. So, this is an old one. So 2005, this thing was made, I think before 2010. So, approximately, so where you would be using to make. So, there are different pronged approaches, they are using in nanoelectronic devices, they are trying to use in molecular nano systems, as well as this is the part where they are using in drug delivery and targeted disease and diagnostics, what we would talk about in our nano biotechnology lecture. This is a kind of an historical perspective. It says this in, if you ask a business person, this is what they these are the revolutionary technology which has changed our life. In the 1800, it was textile, which people started making textile industry, and it changed. It started in Manchester, England, railroad, automobiles, computer, and there is a field that where there would be nanotech, though the primary application of nanotech would be in the field of biology. So, that is why this course is more. So, where is nano skin materials being used? It is cosmetics, and that is where most of the nanomaterials are currently being used. It is used in sunscreen, it is used in any creams what you put in. There is, I would talk about that in my last lecture. In the US, there is also a concern that the nanomaterials are sometimes being added, and you do not know how much toxic effects of that are. For instance, there are places where nanomaterials are added. When somebody goes to the US, one thing you might feel people complaining is if you add a spoon of sugar here in India and you add a spoon of sugar in the US, the sugar is not as sweet over there compared to the one here. Sugar is very fine granules. The other, why is it so? Because over there is something that is added extra to the sugar, which actually does not. What does it do to the sugar? Here, if you keep sugar out in the humidity, it lumps together, it forms lumps. There they put some materials which absorb the moisture, and so sugar you can keep it out, but sugar never gets. So, that is nanoparticles being added over there to kind of keep your sugar dry. You can keep the sugar wherever it is dry, but those are not adding any sweetness to the material. So, that is why you have to add more sugar to get the material out. So, there are lot of places where nanoparticles are being added, but people do not advertise because they are not required by law to say that where nano things have been added. So, that is why like they are added in sugar, they are not being advertised. So some places people know cosmetics, they are put in, actually they are put in, we would talk about when we talk about toxicology, we would talk about they are added in fertilizers. That is why the sudden drive of having organic food, because you do not want to encounter with some of the nanoparticles, because we do not know what happens to the nanoparticles when it comes inside. So, these are the places where this wrinkle free stain fabrics, what you have is, if you wear, in fact my current trouser what I am wearing, it has nanotex. It's nanotex means if you spill something on top of it, it's almost like a plastic or rubber material. So, the thing does not, when it goes inside and you could remove the stain. So, these are places. Sunscreen, this work I was actually involved in working on, we made scratch resistant paints. So, a paints normally on car bodies or other places you can make it scratch resistant. So, these are places where it is nanomaterials being used. Tennis balls, they put nanomaterials inside, so the tennis balls remain hard, because every time you hit air leaks out. They are using and this the same technique on car tires. So, the car tires you do not have to fill air in your car tires, the air kind of lasts there for a long time. Impact of nanotechnology, I will just, this is the business side, you can look over there, all countries are being involved over there. How much investment, just two things you should, things are changing right now. This is an old one. Right now a lot of these countries, Japan, in the actually in Asia, those countries are picking up more, in China more in nano. Okay. So, this was the end of that slide. We would go more, we have more time. So, again, as we know, there was a big future for nano. So, again this was quoted by Charles Lieber. Charles Lieber is one of the most famous nanoscientists. He might get the Nobel Prize sometime soon. He is working on silicon, parts of application of silicon nanowires in the areas. So, the advances in nano biotechnology, this is the place where we are progressing at the speed of light. Every day a new device comes up, new things, new things. In fact, right now I am wearing two of the things. I think you are familiar with this. Have you know this Fitbit? Okay. This thing is monitoring my how many steps I am taking, and from them it is calculating how much calories I am spending. So, that is why, in fact, when Professor Das asked me that whether I need a car to come here, I said no, because if I walk less steps, it warns me that you are walking less. Okay. So, there is another thing I am wearing. This is not the one which is, we are still developing the one. This is right now it is not doing anything, but ideally this would measure my blood pressure. So, as we will walking over there and the information would come in through my phone, I would be knowing. So, I do not have to go to the doctor's office to kind of say where that. So, these are commercial devices which are right now being come. So, that is why I said it is moving at the speed of light. So, very soon in the morning you do not have, people go and take their weight, stand on the weighing scale and know their weight, but right now in the morning they would have all the information there. They would have their blood pressure, they would have their sugar level, they would have their cholesterol level, all sensors would be around. And Google is working in a big way, what is known as Google Diagnostics. So, they will put nanoparticles inside the body, and as it going down it would monitor it. So, if there is a blockage in the heart or an artery, you would know it long before, and the information will be transmitted. So, that is why I am saying it is progressing in the speed of light. By the time I am giving the lecture, there might be 3 other commercial devices which have been already coming out. One of the places where people are working, I will talk about that also, is cancer. cancer diagnostics. But the main problem is nano engineering. The science of nanoparticle is amazing. You can show this can be done, this can be done, this can be done, but what is engineering? You have to do it for the general public to use it. So, every time somebody uses it, it has to do exactly the same thing. Since nanomaterials, nano properties are lot statistical, so we have less control over, and I am hoping that by the time you become more in field, you would be able to control it more. So, that is why this challenge needs to be addressed, both in the field of medicine and in the other areas also. So, in the field of biology, nanotechnology would come in two ways. One way, it would help to monitor things better. In medicine, it still become more of a statistical science. We use the statistical data to find out what would be the results. I will just give you an example. My next door neighbor in the US, he is a robotic surgeon. So, he went to Vietnam to do some surgery. He is a heart surgeon, and he said he did the surgery, but he could not give any anesthesia to the patients. So, I said, why you could not give administer any anesthesia to the patient? They said, to give anesthesia to the patient, there is a weight scale, that if you weigh this much, you have to give this much anesthesia. If you weigh this much, you give this much anesthesia. It is a statistics, but that scale had been taken for the Europeans. So, the minimum of that scale is actually above what an average Vietnamese person weighs. So, the Vietnamese persons could not be administered any anesthesia, because they are below the scale. So, the point I want to make is, and they have to be given the children anesthesia then, but the children anesthesia has other issues. So, that is why they had to be operated without anesthesia. So, that is because the scale was made. Same thing when people do anemia tests, majority of the women in Asia are anemic, but they have a normal life. Why? Because the anemia scale had been decided by the people in the Europe, where people are less anemic. So, that is why that number you are always below. Every time right now people are changing the number where they say that your high risk of having blood sugar. Sometime it was 120, now they have increased to 125. What I say is, with nano things you do not have to rely on that. People are going on what they call is personalized medicine. So, your data would come from yourself. So, the medication, everything would come in, because you would be monitoring it much more. So, that is where your nano would come in. So, you do not have to rely on data taken from Europe and kind of put on, because people have now understood people have different height, different weight, different diet, and so you can't put everything under the same statistical. So, now let us move. So, I hope some of you would be. So, actually last few days back I had gone to visit Einstein's house in Switzerland, and there I realized that Einstein was initially interested in thermodynamics, but he was not very keen, he did not found it challenging enough, and that is why he moved to. So, whatever time we would have, we will talk about what the nanoscale, how things change in different length scales. In mechanics, we have Newton's law and gravitation. In fluid mechanics, Navier-Stokes equation. In electromagnetism, Maxwell's equation, and thermodynamics, we have the laws of thermodynamics, and in optics we have diffraction and interference. This is for macro scale things. How in nanoscale these things get modified, we would talk about that. These are basically the fundamental things which guide all different branches. Now, as things I kind of gave you an example of that a little while before. So, these when different. Now, we talked about, they have different names. We talked about the in fluid mechanics or a lot of these we assume continuum substance. Even in Ohm's law also we assume continuum, that means electrons are flowing, there is no dearth of the amount of electrons that flow by. But that assumption, the continuum assumption, fails when we work in nanotechnology, and that is one of the reasons why we have to come through. These are all the different names of different type of micromechanics, nanomechanics, molecular mechanics, they all have come in over there. They all get their name by using some of the models of continuum substance and using it for quantum mechanics. In quantum mechanics, how many of you do you know quantum mechanics? So what does quantum mechanics, which regime does quantum mechanics work on? It only works for atoms. In fact, there is only one problem which quantum mechanics solves exactly, and that is hydrogen atom. Anything else quantum mechanics cannot. It is a very big thing set up, but it also have to approximate to look at solutions. In nanotechnology what it does is quantum mechanics cannot be applied because just for hydrogen atom, that is the only one it has solved, is because it gets so complicated with more interactions, you can't. So for nanotechnology you have to do a combination of quantum mechanics and you have to put some statistics in it, because in nanotechnology you do never work with one atom. What was the size of one atom we talked about? Less than a nanometer. So and 1 nanometer was in the order of at least 10 atoms, or it would be having more of that, and solving a problem for 10 atoms with quantum mechanics would be a tremendous big exercise. So that is why there we use parts of statistics and we use it part of continuum. So that is what we are. So the science also has to be developed. So this is what I say is how difficult for a system containing a tube of 25 millimeter on each side. Okay, how much time? So how we would be handling this. So looking at this problem from both microscopic and so a 25 millimeter of each side containing the gas with atoms. So we would be solving this using a macroscopic model. What is macroscopic model? The 4 Newton's law, Maxwell's equation, Navier-Stokes and what we mentioned over there, and we will try to solve it by using microscopic. So on the basis of the microscopic we have statistical considerations and the probability theory. So we have to say we will talk a little bit about quantum mechanics. One of the basic postulates of quantum mechanics is you cannot specify the position and the energy or the velocity of the atom of an electron, whatever you are looking at it, with the equal amount of accuracy. It is known as Heisenberg's uncertainty principle. The reason behind that is, how do you find the position? How are you looking at the position of this? Light comes in, hits this surface, comes back. What are you assuming here? That when light comes and hits this, it does not move the position of this, it stays where it is. That assumption is fine as long as it is big, but when this becomes the size of the light, so it is like one ball hitting another ball, then the light will come, reflect back, you would know, but then this wouldn't be at that position. So you would know what it was before, so you wouldn't know where it is right now because it has hit and this thing has moved. So that is what the uncertainty is. So that is why what we have to look at is probability. We have to say, because everything is uncertain, so we have to say there is a chance. So that is why when we use microscopic theory we have to use what we call is theory of, we have to find the probability and we will find out. I gave you example of the pi bonds. When the electrons are over here, I have said the pi bonds are sticking out, again that after calculating we have found that is the maximum chances, the probability that the electrons are actually right over at that position and not anywhere else. Again it is not guaranteed that if you go over there you will be finding all the electrons, but that is the probability. So, the macroscopic thing is again based on handled on the continuum assumption, which kind of breaks down and how we would be taking. So, we deal with the time averaged, we can use this time average influence of. So, these macroscopic average can be by our sense, whatever we can measure is with our instrumentation. In nanotechnology we are trying to use our lot of these things we cannot measure it, we have to see what are the final effects of it. So, that is why it is a little difficult in imagining. So, the breakdown of the, so as the materials become smaller, that is why what I told before, this is the breakdown of the continuum model. So, what we would try to use is we try to use, still we are using macroscopic properties and we are trying to define our nanomaterials based on nanotechnology based on that. Pressure for that instance is a macroscopic measurement. How do we measure pressure? Molecules come, hit the walls, come back, hit the walls, come back, we see the energy transfer and kind of an average over there. Ideally if you see a few molecules, pressure will not be a very proper way of measuring. If pressure is assuming in this room there are enough number of molecules, they are hitting the walls and coming back, so there is no dearth of the number of molecules. But again if number of molecules become small, then pressure may not be the proper way of kind of characterizing what is happening, because we might have to look at something else to, but that is I am just putting a question mark on these just to give you an idea that we are still borrowing entities, because we do not have something which is defined for the nanoscale. So, we have to use whatever is available to us, but we have to keep in mind we can't just take it and put it in the equations or whatever we know before, because sometimes we would find out that it would not predict what we are looking at in experimental sense, and that is the main reason is because we are using tools which are not actually applicable for the nanoscale. So, billionth of a meter we this is just a brief introduction to quantum mechanics, which basically tells. So, quantum mechanics has two postulates. What does quantum mechanics tell? The name quantum means it in jumps. Okay. So, quantum mechanics what it tells is the electrons as you go smaller in size, as I said one of the postulates was what we talked about, the uncertainty. So, we cannot find the position and the movement, the velocity of the electron simultaneously at the same time. The other thing is if we go smaller, if we go in energy, or if we suppose this material has water, as we cool it down, how are we measuring the energy of this water? Thermodynamically we can insert a thermometer over here, we can find the temperature of it. What is caused by the temperature? The molecules are moving around, hitting, and it is causing that temperature. But as we cool it down, if you want to find the energy, what we would find out that the quantum mechanics says that as we lower down the energy, the energy is caused by number of say with temperature. As we lower the temperature, the energy goes down. What classically it says, as if the temperature goes down, the energy would go down, so it would be going down continuously. But as we go into the quantum regime, the energy would not go down continuously. It would be, if you have 1 or 2 atoms over there, what would happen is energy would change like a step. That means up to a certain level energy would remain the same, then if the temperature crosses over to a certain level, then the energy would jump on to the next level, then it would stay the same, then it would jump on to the next level. So, but as the energy goes more, because there are more number of electrons over there, so each one of them are going like steps, so it becomes an average. So, suppose you have number of steps and they are slightly displaced from one another, if you take the average, then it would look like a ramp. So, a ramp is what is a continuum theory, a ramp is kind of a slope which kind of goes up, but as you go down you would see in the quantum mechanics they goes in. So, the way we try to use quantum mechanics is, instead of using Newton's law, we would still try to find our, what is our ultimate aim. Our ultimate aim is to finding out the energy, because everything we try to relate it from the energy point of view. So, to find the energy, normally in classical mechanics we use the energy equation, potential energy plus kinetic energy is equal to constant, or potential energy, kinetic energy, thermal energy is equal to constant. So, this is the equation which I have written down. This is another way of writing energy equation. So, what we assume, we say that why is not it going back? Okay. So, this is basically equivalent to the F equal to ma equation in quantum mechanics. What does it says? It says we have, these are what we call the which wave functions, which basically gives you the probability of where you would be able to find whatever you are looking for, and this is the and you would be finding the energy. This is basically an energy equation. This side it tells you the kinetic energy, and this side it will tell you whatever the potential energy of it is. So, anyway, you do not have to know all details of that. You actually basically you solve these, this is this differential equation, you solve the wave function, and then once you find the wave function, you would be, this comes under different names. People call it the Schrodinger equation, some people call it, there is if you write it for each and every electron for different states, you would be they come in, it can be also written in a form of a matrix, like each equation can be written in a matrix, and when you solve for this, you get the total, this E what we write over here is the total energy, which is if you write this in a matrix form, it comes out as the eigenvalue of the matrix, or it means you are trying to find the constant which makes this the differential equation. So, this is what for, again, for semiconductors, when we look at it, we write, you see this side we have written the potential energy, here we had written the potential energy for a free electron. Free electron has just energy moving by itself. Now, when an electron moves inside a material, it moves inside a lattice, the lattice itself puts some constraints on it by putting some more energy rigorous. So, that is why here this extra term what we have put in over here, this is the energy that comes in because of the lattice, the other. So, as we solve these, basically the energy, if you look at the energy, they have the same form over here. This is a special constant which shows up over here, which is known as a Planck's constant, but what it shows over here is that the energy is given by this, where this k actually, as you move from one level to the other, this k keeps changing, which means that the energy does not, k is not a continuous function. So, that is why energy kind of goes up, but if you change from 1 to 2, the change of energy is lot more. If you change from 100 to 100 and 101, the change of energy is very less, and it gets more to the continuum change. Okay. So, this is what happens for semiconductors. For semiconductors, again we solve this, the extra energy, what happens is this gives rise to the electron gives an energy. This actually gives what we the energy gives rise to what we call as the band structure of. So, what happens is electrons when you solve this for semiconductor, over here every electron can have any energy what possible, but because of this there is a certain region where the electrons for certain values of k it will have a certain. So, what the band structure what it says is the electrons would be all in a certain area, certain electrons having some energy would be in an we have 5 more minutes, do we? Okay, we just got so these when we move from so what we are doing over here is we added the extra potential, that this one the V. Now when we go the electron behavior, when we call it by different names, the quantum well, the quantum wire, the quantum dot, that means it is 1D confined in parallel to. So, in one dimension the here when it for a free electron when it is solving it is having this is the how the wave looks like. It can go from any value to any value for any time. When we put in the extra constraint of the extra potential, the wave kind of has, but it is kind of restricted, that is why it is known as block wave. It only happens in between the two electrons, there is a certain space where that means over there the probability of the electron was anywhere. If a free electron is present over there you can be any, but once you put potentials over here you are restricting it. So, that is why now the chances of it at finding at certain places are higher than finding it at some other. So, that this is what is known as block wave, that is what it is saying. It comes in because we add an extra potential here. Now, when things go into the nanoscale regime, then because of what we say the surface properties coming in more. Right now when we talked about this did not talk about what happens in the surface, but when we make things more smaller, then what happens is along with this the surface forces and everything come over there, which we put in as an extra, and so that is why our electron distribution kind of changes. So, at certain places, because earlier for semiconductors everything had a certain electron distribution, but now electron distribution again and that gives rise to all the properties that comes in. Now, where the electron gets confined, that is from where the name comes in. When we call a quantum well, the electron is one dimension, it is confined in parallel plane in quantum well is one dimension confined and in a parallel plane in 2 dimension. So, that is where you have the maximum chance of finding the electron. Then in a quantum wire, and I think Rahul or Rohit said that for a quantum dot they are confined in, so the electrons are confined in all those. So, there is a high probability of finding the electron over there. So, that is why when you shine light over there, because all the electrons normally for any material there are certain electrons over there and then they are moving around everywhere. It is like going to a school where the discipline is very less. So, in a class some students are there, other people have bunked the classes, there are no. So, at a certain time if you want to do something in that school you will only get a part of the students involved, but if you go to like a military camp or a quantum material is almost like a prison where everybody is enclosed over there. So, you would get everyone involved over. So, a quantum dot is it is confined in all 3 dimensions, quantum wire they are confined in 1 dimension, the other material. So, that is where all this behavior comes in, and that is because since the electrons are only found exactly over there. So, that gives some extra properties of the nanomaterials. I think that is what we talked about. So, when just let me tell just why are we interested in nano materials. I think we have taken electrons in semiconductors are easily controllable and accessible, yet poor inherent performance. The electrons, to make our semiconductors, we have to keep our computers in a room which is air conditioned, which is cold. Why? Because as we cool down the temperature, we can make the electrons more controlled. But when we go into the nanomaterial systems, electrons are already controlled. So, that is why if you want to use a computer inside a human body, we would be able to use it for nanomaterials, because there we have already confined the electrons. We do not need to cool the electrons down, so that they can be confined and we can use that. So, that is where we are interested in materials. When we make materials smaller in size, these are something which inherently comes in by making the material smaller in size. So, it is not only the size, what I am trying to say is nanomaterials have certain properties that makes this a special branch. So, you have to know what happens when things becomes that small. So, we take the advantage of both semiconductor. So, geometrical dimensions in the artificial structure can be tuned, relaxation and dephasing process are slowed. So, wherever we want to make speed, when the electrons, when we apply light, when we apply energy, what happens? Thermal energy comes in, electrons jump from one level to the other. Here we can control it. If we can control that, when it will jump from one level to the other, we can control more. For example, we can make our light more into, our LED produces more light than our normal incandescent lights. Why? Because in an LED we have made the electrons all of them to function the way we would like to. So, that is what happens for when we are making it into the nanomaterials. This is this we talked about the D, the confinement length. You can learn we can make arguments with, this is for thermal energy. Thermal energy is proportional to the temperature, and so the temperature change the again the eigenstates are the word which we use is when the electron go in one level for going to the next. Okay, I think I am overshooting my time. Okay, so I think we should take a break now, and then we come back and we talk about nanobiotechnology. We can talk a little bit about this one also. Okay. Thank you.
Please raise your hand. Dr. Sarvarao, Gurpreet Singh, Mala I, Annapurna Devi, Raju Poddar, Sumit Kumar Dubey, Vishal Dev Ashok, yes, Provin Ji, Apradip Nag, yes, Ajay Kumar Shahi, Amlesh Nanda, yes, Amit Kumar Singh, yes, A.S. Ruby Chelsia, Adresh Kumar Verma, probably absent. Adresh Kumar Verma absent. Nipasha Karmakar, present. Gaurav Kumar Dan, Gaurav Kumar Dan, Vishnu Priya, present. Lin Dima, Mustakalem absent. Nirupam Siddhar. Then Pratibha Agarwal. Pratibha Agarwal. Rigjati Hati. Rigjati Hati absent. Acha Rohit Sattam.
Present.
Sajita Saha. Sajita Saha absent. Shobhit Bhattacharya. Okay. Then Subhotri Talukdar. Subhosri Talukdar. Subhosri Talukdar absent. Jaya Sudhanga. Jaya Sudhanga absent. Acha. Sushobhan Daloi present. Anga Pandi. Anga Pandi. Vishnu Kumar.
Yes, sir.
Vivek Chetri. Anjali. Arpon. Arpon. Gaurav. Jyoshna. Pradeep. Yes, Pradeep. And Kamal. Anybody left? You. What is your name? E.T. Sharma. Yeah, that is due to the ERP problem. I'll take care. Sure. Do you have the registration number right now? No. Okay, I'll take. Any other? Deepak. Institute, again, probably I am not getting your name in the area.
But
Yeah, but now, right now, I'm Deepak. No? Any other name? Hazardon has registered, no? Thangapam.
Yeah, he came last 2 days. He came.
Okay. So about 10 minutes break. Okay. Tea break and then we again.
People have not given the food preference. Please give today, sir. In this list.
আমি তোমার কয়েকটা ফর্ম আছে ফিল আপ করতে হবে।
Food preference. Veg or non?
এইটা তোমার
আজকে কি আফটারনুনে
আফটারনুনে এদের ল্যাব ভিজিটে মানে ধরো তুমি যদি আমি আজকে ইয়েতে নিয়ে যাবো ডিসি অফিসার প্লাস দিনের সাথেও একটু
আচ্ছা আচ্ছা
একটা কাজ রিসিভ করবো।
ঠিক আছে।
ধরো তুমি যদি 4:30 নাগাদ আসবে,
হ্যাঁ আমার তো ফ্রি আছে।
4:30-র সময় আমি এদিক থেকে তাহলে একটু ফ্রি থাকবো, তখন দুজনে একসাথে যাবো।
আচ্ছা আর আপনার ল্যাবের সঙ্গে
ল্যাবেতে তো না, তুমি চলে আসছো। আমাদের ল্যাবটা তো শুরু হচ্ছে 3টে থেকে।
হ্যাঁ
ল্যাবটা শুরু হচ্ছে বলতে এদের 4টে টিমে ভাগ করে দিয়েছি, 4টে ডিফারেন্ট লোকেশনে প্রতিদিন এক একটা গ্রুপ যাচ্ছে।
আচ্ছা হ্যাঁ
ঠিক আছে, এর মধ্যে আমার ল্যাবও আছে। ইউ ক্যান কাম বাই 3, নো প্রবলেম, ইউ ক্যান জয়েন।
আচ্ছা
তুই যদি এসএমএসটিতে চলে আসো,
হ্যাঁ
তাহলে ওখান থেকে ওখানেই আমার ল্যাবটা আছে। আমি একটু অন্য ইয়েতে যাবো, আবার অন্য দুটো।
ঠিক আছে, আমি 4টে নাগাদ আসবো।
তারপরেতে 4:30-র পরে আমরা একটু
ঠিক আছে।
যাবো। তোমাকে আমি এই দুটো এখন দিয়ে দিচ্ছি, তুমি যতটা সম্ভব ফিল আপ করো বা দেখে নাও,
হ্যাঁ
যদি কোনো ডাউট থাকে তাহলে বিকেলে সেই অফিসে ওখান থেকে ক্লিয়ার করে নেবে।
ঠিক আছে।
এইটা দেখো অনলাইন নিয়ম আরেকটা আছে টিএ, এই দুটো দেখে ইয়ে করে যাতে আর তোমার যদি কোনো ডকুমেন্টস দিতে হয় দিয়ে দিও।
হ্যাঁ
আমার কাছে এই দুটো তো তুমি পাঠিয়েছিলে, এটা
হুম
আর আগে বোধহয় আরেকটা কিছু পাঠিয়েছিলে,
হ্যাঁ
এটা আমার
আগে
মনে হচ্ছে সেই অফিসে দিয়ে দিয়েছিল।
হ্যাঁ হ্যাঁ আগে আগে পাঠিয়ে
একটা
না,
কিছু বোধহয়
আর
পাঠিয়েছিল।
এটা হচ্ছে ট্যাক্স রেসিডেন্সি।
এটা আমি তো তাকে পাঠিয়ে দিয়েছি আর মেলেতেই থাকবে। তুমি সেই জন্য আমি তোমাকে এখন দিয়ে দিলাম, যদি তোমার কোনো ডাউট থাকে বা ইয়ে তাহলে সি অফিস আমি তো বলতে পারবোই না, সি অফিসই বলতে পারবো।
আচ্ছা আচ্ছা, এগুলো তো আমার মানে দেখে মানে
হ্যাঁ,
এই বলতে
সেটাই।
ব্যাংক
হ্যাঁ।
সুইফট নাম্বার আর এগুলো মানে
আর ওই যা যা ওইগুলো নিয়ে একেবারে নিয়ে এসে
হ্যাঁ
ওই যে কী বলে তোমার বোর্ডিং পাস হ্যাঁ দেখো ওটা
হ্যাঁ হ্যাঁ
bill
বোর্ডিং পাস।
হুম।
তাহলে ঠিক আছে, এই দুটো আমি তো এই যে সামনে যে এরা আসছে না, এটা কি আসেইনি না, এরা কয়েকদিন ক্লাস করে
না
দেবে?
এরা হচ্ছে অ্যাবসেন্ট আছে, মানে ওরা রেজিস্টার করেও আসেনি,
ও
রেজিস্ট্রেশন করেছে ইয়ারটিতে,
হ্যাঁ
কিন্তু তারপরে তো আসলে আসেনি কোনো কিছু। দু একজন আমাকে জানিয়েছে, তিনজন জানিয়েছিল যে আমরা আসতে হচ্ছে পার্সোনাল
আচ্ছা 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 আচ্ছা।
রেজিস্ট্রেশন অবধি করেছে।
তা ওরা কি সার্টিফিকেট পাবে না নাকি?
সাতজন না পাবে না। সেই জন্য আমাকে এটা ওই সি অফিসে বিকেলে গিয়ে দেবো, ওরা
হ্যাঁ।
সার্টিফিকেট তৈরি করে দেবে তো,
হ্যাঁ।
সেই জন্য লিস্টটা দিতে হবে।
আচ্ছা, আর ওদের কি ওই যে পরীক্ষা হবে, পরীক্ষার বেসিসে কি ওদের কি কোনো গ্রেড হবে নাকি?
এটা হচ্ছে মেন যে ইয়েটা হচ্ছে আমাদের আইআইটি স্টুডেন্ট।
হ্যাঁ
এবার আমি এদেরকে কিন্তু বলেছি সবাইকে যে ইউ জয়েন
হ্যাঁ
এক্সাম,
হ্যাঁ
এরপরে যে ইভালুয়েট করবো,
হ্যাঁ।
করে যদি গ্রেডটা হবে সেটা জানতে চাইবে তখন, কিন্তু সার্টিফিকেটে জাস্ট পার্টিসিপেশন।
আচ্ছা আচ্ছা, এদের হোস্ট ইনস্টিটিউটে ওরা ক্রেডিট ট্রান্সফার মানে দেখাবে দেখাবে না? হ্যাঁ
না আমাদের আইআইটি স্টুডেন্টদের কিন্তু লাগে।
আইটি তো 4 জন আছে বললেন না?
Sorry to bother you. I just
No,
have
no,
a few
no.
questions.
Sure.
You were talking about nanoscale bulletproof clothing, right?
Yes.
I have a question.
Yes.
In conventional bulletproof vests, which I've been personally seeing,
Yes,
they have metal plates to take the impact of the bullet.
that's
So
right.
that, but then in the clothes, it's just like this, right?
Yes.
So what about the impact factor over there? When a bullet hits you just like that, that would be the impact.
No,
force.
this thing is working as a steel.
Oh, right.
So why
that
does the
would
why,
be-
why does the steel deflect the bullet? Because you see, it's a change in momentum.
No, but the steel accepts the impact, right?
Yes.
It takes the impact. Even
Yes.
though we wear the vest, we can feel the impact. But then without so much thick layers in
That is the nano materials can take.
withstand.
For example, carbon nanotube. It is like a banana plant.
Okay.
You know, it takes the thing, it bends,
Okay.
and then it takes the shock and.
Alright. So there would be no problem for taking the impact. You won't
No,
feel the
no, it won't be. What I said is a slight an exaggeration. It won't be like a shirt like this. It would be maybe like a jacket.
Okay.
So slightly
So I was
thicker.
wondering how have we
Slight-
gone into technology so well advanced that it became so light? So that was what my thought process.
Yes.
was.
So it is like what you can think is inside your jacket. You can sew in a nano nano mesh layer. So when it comes in, the main purpose of that is it will take the impact, and then because it's so many materials, each of them kind of shares it. So that would, if it's any other material, the impact would be faced by that one, and it won't be able to transfer the impact.
Alright.
So the way they are trying to do is taking the impact and transferring.
And there was this another question. You said nanotubes are very small; they can't be connected, right?
They can be connected,
No,
but
they can be connected, but then you said it is not
it-
as strong as
yeah,
the
that's strong.
natural.
Yes, yes.
So why haven't they developed? Just what you were telling is just directly joining like these, or with any other.
When the way they are joined
Because
is,
I'm a biology student and I have no relation to nanotech. But
No.
recently I wanted to take this course because we are working on a nanomedicine.
yes.
I'll
So-
come to
so-
that part because that's my final
Yes.
question.
So what they do is when it's like spinning a yarn. Like when a nanomaterial comes out over here, they spray some glue onto that, and the next layer comes in and joins. But they cannot guarantee they will be joining like this. It can be joining like this.
or any.
So that is why it.
But won't they, if they are joining like this, won't there be a strong force over here compared to the other part?
Yes, if it joins like this, it would be better. Like writing, joining like this. But there is no control of what is happening. So mechanically it is okay, but the problem comes when they are making it electrical. So electrically, this and this, there is a difference in our electrical. So mechanically, that's the reason why airplanes they have been able to make with composites or cycles. Where I don't know whether you have seen the guys who ride the Olympic cycles. The weight of a cycle is less than 1 kilogram.
Oh, okay.
You can lift a cycle up. It's almost like this book.
Right.
It's so light, but they are very strong. If they fall down and all, it doesn't break. So this part they have been able to do. For a cycle, it does not matter that much.
In US, people have also created this tubeless tires that you don't know.
Yeah. That is the same concept. Yeah. Now even in Indian cars, I don't think you have tubes.
Yeah, one or two very highly expensive
Cycles are
high-end
still.
models.
No, cycles. They are
A high-end model like Firefox, they give you that, but it's extremely.
yeah. Their cycles also don't have tubes.
But they're extremely expensive.
No, normal cycles also they don't have.
I've never seen that.
Yeah, they.
And my final question is, I was reading because for our work had to do some base work on nanomaterials and nanosciences before
Yes.
going into the actual work. So while reading, we got a point that whenever you do a nanomaterial synthesizes or
Yes.
when you're converting a material from macro to micro level or
Yes.
nano level,
Yes.
the property gets enhanced. That's what we were taught. The property
Yes,
gets
certain property gets enhanced. Means it depends on which
It's
property
not always
it is. Which property you're
I was
talking.
talking about the biological aspects of it.
Yes.
So when we did, you can call it as an antimicrobial assay.
Yes.
When we tested the drugs directly,
Yes.
it showed good amount of
Yeah.
inhibition concentration.
For that biological context, it enhances is because earlier you're actually making the reaction more.
Yeah, but then when we did it on a nanoscale, the reaction was nil. We found the growth to be excessive, not even excessive. The growth was normal, and we were shocked that when it was given as directly as a drug,
Yeah.
it inhibited, and when we gave it in a nanoscale, it didn't show any inhibition. That led to a question whether we did some mistake.
No,
But
that
we-
is means there
we
could.
twice did
If
the experiment.
you have to know, you know homeopathy.
Yes.
How does homeopathic medicine works? That's nanoscale.
Okay.
So normally if you make things more concentrated, you would expect things to work better.
Alright.
In homeopathy, it's just the opposite way. It's actually you're making things dilute.
Alright.
But
So maybe
again it depends on the forces in the solution which is holding it together, and the nanoparticles for one material it might work, for other material.
So what is the possible suggestion is like we can reduce our concentration on check because we were going from 30 to 100,
Yes.
and in a normal scale it showed an inhibition, but in a nanoscale it was way out of league. So
Yes.
maybe less than 30 could give us.
Yes, there could be a point where I can tell you my experience. I was finding thermal properties, thermal conductivity of materials. So thermal conductivity we were trying to work. So we are trying to increase the thermal conductivity of water.
Alright.
So we put some copper nanoparticles in it.
Okay.
So if you put copper nanoparticles in it, you would expect that copper is a good thermal conductor.
Yes.
The thermal conductivity would,
Yes,
would,
exactly.
would increase. But we found the thermal conductivity actually
It went down.
went down. It became more, and after a certain concentration,
No.
then it was a behavior which changed drastically depending upon how much of the copper particles you added, what was the size of the copper particles which what we added. So if you add too many copper particles, you are actually the actual. So the scale is, so you have to do an experiment over the concentration, and if you can vary the size, you vary, or at least vary the concentration, and you can see, means looking at one part of the concentration, it might be like a U-shaped curve. Up to a certain part, it goes down, and then after it crosses a threshold, then it goes. Because talking about the surface and the volume, so as you make it bigger, the volume is increasing, and that is the property of nano. There is no gradual change. If the volume changes over 60% of the surface, then suddenly the volume forces pick up, because the volume forces are R cubed. So they are a lot more stronger. So even if you have a few more to it, they will act resent. So that's why there's a sharp change. So my suggestion would be you try other concentrations, and maybe in that concentration. No, this is fine. There is no sugar, is it? Or
No sugar.
no, this is fine. Thank you.
You don't take sugar, no?
No, I don't take sugar.
Okay.
Okay, thank you.
Thank you so much.
Yes. And please ask me more questions. I
No,
would.
because we were quite confused with, and our guide was like, he is from plant biotech. He was said, this is your idea.
Yes.
You have to work on it. I can't help
So
you.
plus one point of time, I want to just introduce myself. I'm Madhavan. I'm coming from a 9 city same.
We are working on the same project.
Yes.
So plus I had a doubt. For example, if you synthesize nanoparticles from plant extracts, they're always telling aqueous extract is better for synthesis because water content is meant for nanoparticle synthesis.
Yes.
So if you go for other extracts like ethanol, chloroform, and other
Yes.
synthesized nanoparticle from it, the stability of nanoparticle is very low. Within a day, it is getting sedimented.
Because for aqueous extract, we tried the nanoparticle synthesis. It
Yes.
stays along with 1
1
month.
month.
Yes.
For
It's
us.
been nearly 1 month since we synthesized, and last time we checked like 2 days ago, it's still stable. But then,
Can you go and outside and talk, because inside food is not allowed.
Oh, I see.
Sorry to.
Okay.
Come.
Okay.
we'll meet
Or we can ask the question after the session. Yeah. Can I have another cup, please? It's a little hot.
We will circulate that also.
You switch off your microphone.
Oh, it's on as I was. Oh, sorry. Sorry. So everything was being recorded.
No, now they have switched off.
ও আচ্ছা আচ্ছা ও সরি হ্যাঁ ঠিক আছে ঠিক আছে আচ্ছা
Up to the Saturday, and I think we have to start it.
Okay, so some of you had questions and asked me at the end, so I would be very much glad if you ask me more questions. You can ask me questions while I'm giving the presentation. Also, if you have questions about something, or after that, I'm available after the classes or during the break. If you have any particular questions regarding to some work you are doing, I would be also glad to address it if I can. I think in the previous slide I had a kind of a Venn diagram type diagram, which I just now we moved to this one, which shows that nobody can be a true expert in nanotechnology. The reason is it is so multidisciplinary. So, nobody, if somebody has claimed that they are an expert in nanotechnology, then they are bluffing. So, you have to have a particular aspect what you would be doing. So, the last slides, I think a few of them which we were talking about, the temperature effects of what happens because of temperature, the nano. That I think you can read it. There are a couple of before we go in over here, can you answer a couple of questions from the first slide, so that I know that you have. Okay, so what are some important characteristics of nanomaterials? Okay, can I? Yes, everybody is saying, can I? Yes. Surface properties dominate the bulk, that is right. And why, and because of that, what happens? Yes, so what is the effect of that? The properties, whatever properties we kind of associate with the materials, those properties are not the same. For instance, we know copper is conducting, this material is translucent, it shows light, and all those properties keep changing primarily. What are the other problems of not problems, but other properties of nanomaterials regarding our knowledge of applying concepts or theories behind it? For example, Newton's laws or Ohm's law or Maxwell's equation. Is the problem is the continuum model breaks down. So, you cannot use, that means there are not lot of electrons or atoms available. Means whenever we study whatever we know with be it in circuits, be it in thermodynamics, be it in mechanics, we never think that there is a dearth of electrons. but in nanomaterials there is not a dearth of electrons, but obviously there is a limit. So, that is why we have to consider that also, and since it is small in number, by changing our properties we can concentrate whatever is available. It is like somebody who has crores of rupees. So, that person can spend money there, that is our normal bulk material. But if you have your resources is limited, say you have only 20,000 rupees. So, you would try to spend it wherever you need the most. So, nanomaterials are like that, they have less electrons, but if you want you can use all of them for your need, and that is why you can accentuate some of the properties. Somebody was asking me that nanomaterials kind of increase the properties, and that is the reason why it is increasing, is because you are putting your entire resources on that, because this is finite. So, right now I will talk whatever I will talk about in this lecture, we would talk more in our in each of these sections in our later lectures. Okay. So, what is nano biotechnology? So, it is, again we talked about multidisciplinary, everybody plays a role over here, physical scientists, biological scientists, engineers. I put medicine in general, it involves anybody working with medicine or related medicine, and then pharmacists. So, these ones we already went through. So, let me this is we would be using this nomenclature. So, that is why I wanted to show you. People try to put the word nano, it's right now it is a marketing thing. So, the word nano is being used. Apple calls their device nano, Tata calls their car nano. So, everybody wants to call nano, anything little small, it is a marketing gimmick. So, but what is nano is currently this is something, I think the nomenclature which you should be. So, first of all, the nano is normally we use for with anything in the diameter of 100 nanometer to 1 nanometer, we call a nano wire. It is, what is a nano wire and what is a nano rod? You can use this term. Wire is flexible, okay. It is something, nano rod is something which is rigid, which is, again, how do you make a nano wire and how do you make a nano rod? Normally the same material does not, if a material forms a nano wire, it does not form a nano rod. If a material forms a nano, what dictates that? It is basically its position in the periodic table, or what are the electronic configurations over there. Okay. So, most materials form a nano wire because they are flexible. Nano rod, I think there is a particular type of zinc oxide which forms a rod. Then the other name we call it is a nanotube. So, difference between wire and tube is a hole. We just gave example of carbon nanotube. So, carbon is an example of tube. Then there are some materials which are called as nanotapes. What is nanotape? When you take the cross section is not a circle, cross section is a rectangle. So, it is like a tape. So, it is again some materials form tape structure. Zinc oxide, for example, has a nano tape structure. Okay. So, that is, then springs, you can make things which are coiled and helical structures. There have been people have been tried to make protein molecules in form of springs. So, that why do you want to make it in a spring structure? If you want more part of it to be active, reacted, and you can get it into, the main idea is the nano wire has maybe this long, it has places, if you make it into a spring you can compress on the size and you can try to have more of it taking part in the reaction. Again, you cannot make nano spring. You cannot start with carbon nanotube and make it into a nano spring. It is decided by its chemistry, its position in the periodic table. Then these are outliers, that is why I put it in red. People normally sometimes claim this as also being nanomaterials, but these are not nanomaterials. Nanofiber and nano whiskers. Nanofibers and nano whiskers are normally have the same tube like or wire like structure, but their dimension is lot bigger, they are in the micron range. Whiskers of silicon, and they were people worked with it even in the 1960s. Then also we call it nano rope or nano bundle. Rope and bundle is very rarely you have one nanotube material together, you would have number of them combined on top of it. So, that is what is nano rope or nano bundle. Then there are some interesting new structures which found which are something is known as nano bud. What is nano bud? This is the place I told you there was a big issue of making contacts with nanomaterials to the real electrical circuits, because nanomaterials are so thin. So, that is where this nano bud comes into the picture. What is nano bud? It is like an anchor. If you take a boat and if you want to anchor it at a certain place, you take the rope and then have a big thing that is kind of anchored. So, nano bud is you have a certain structure which is a big shape and it anchors on one side to the nano, and on the other side you can make it contact with the bigger. So, you are kind of using it as an interface. So, what is nano biotechnology? Again I had a kind of a problem. Yes.
So, I have one question regarding the nomenclature. You are talking of the nano rods or nano wires.
Yes.
Is it confined to carbon nanotubes or to all the nanomaterials like single nanoparticle based on single metal?
Yes, yes, it is.
Or
yes, 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 yes. It is. This is the general name. Nanowire. Normally, if you have metals, for example, copper, gold, and all, they have nano wire form. Okay. Nanotube is only carbon and boron nitride. These are the two. That's boron nitride is a ceramic. So, these are the only two materials known to have tube. Everything else is normally a wire, nano wire. Say silicon is nano wire, germanium is nano wire, aluminum is nano wire, everything else is normally a nano wire. Zinc, and then there are a couple of ones which also form rod. Okay. This nomenclature is in general. Okay. In general for one dimensional nanomaterials, anything that forms 0 dimension or 2 dimension, there is a different nomenclature for that. This is everything that. Yes.
The same nomenclature is defined for 0, 1 and 2.
No, when you tell nano wire, it is not for 2 dimensions. We normally call nanoparticles or quantum dots when we talk about 0 dimension, and when it is 2 dimension, other than graphene, nobody, I think you do not have a name for the other materials. Okay. Because initially historically nanotechnology started with these materials and everybody started calling it by their own name. So, that is why the confusion is. The nanoparticle, when I will talk about the impacts of toxicology impacts, EPA is Environmental Protection Agency in the US. They have a name, they have said, because everybody was trying to use the word nano to there. So, anything in the size of EPA regulation says if it is below 250 nanometer, they call it a nanoparticle. Anything above 200, even if it is 251 nanometer, it is not a nanoparticle. So, that is the, again scientists do not see that, that is how the lawyers kind of look at it. So, if you are claiming your material to be a nanoparticle, it has to be below, average diameter has to be below 250 nanometer according.
Say that like if the particle size is like more than 100 nanometers, it comes into mesoscale. They say that like we have something like
yes.
above 100 nanometer as mesoscale and below 100 nanometers is like nanoscale.
That is, again, there are a lot of people who have been working in this area. The word nano and all started coming in the 1990s. Before 1990s, it was not that people started suddenly working over on this. People used to work on this before. In chemistry, they used to call it colloidal science. So, people used to work with colloids. So, if you work with colloids, lot of them are in this dimension. In physics, people used to call it as what she said, mesoscopic physics. So, mesoscopic physics was something in between atomic physics and the real physics. So, the regime in between, which lot of it is actually nanomaterial. So, once the word nano has come in, now everybody has called have taken the word nano. Again this I call this nano biotechnology, also some people call it the other way also, bio nanotechnology, and again it depends upon whom you are talking to. It is a mixture of biotechnology with nano. So, what do they do? First of all, it uses of nano devices for doing biological measurements. Unfortunately, the field of biology when Robert Hooke discovered the microscope. So, that is that was in 1800 something, 1900 I think 1800 something. So, after that, or even before, I think 1600 something, I forget, 1600 something, yeah, because Robert Hooke and Isaac Newton were actually rivalries, okay, rivals. So, in fact, Newton's law was part of it was developed by Robert Hooke, but we do not know his name because Isaac Newton kind of he was. So anyway, so that is why Robert Hooke went for microscope, that is a different story. But Robert Hooke, after that till now, that is the primary tool for biologists. So, nanotechnology would try to give us new instrumentation, new tools, so you could learn more. I just said biology is still an experimental science. So, we would try to learn more about what is happening, and we would be able to do that. So, that is what nanobiotechnology is. The way I say it is biology is at a stage right now what chemistry would have been if Mendeleev would not have discovered the periodic table. Okay. So, if there was no periodic table, every compound you would have a different belief, different thing. So, you still do not know, it is kind of more of an experimental science. So, biology is still in that level. I am expecting from genetics we would be, it may not be as short as the periodic table, but with all this instrumentation very soon we would be having a way where we would find what is the thing that is same between a human being and an ant or a virus, and the way it is looking for, like in chemistry compounds, everything is related back to the periodic table. So, nanotechnology would play a big role, nanobiotechnology would play a big role in doing that, because we have been using use of biological materials as macromolecules and nano devices, that is again that people are trying to work on it. There are devices which get into the human body, pacemaker, other things which get into the human body, but they still use standard materials, silicon, copper and all these, and those are the reasons why they get, sometimes they get infected, they have problems with the body rejecting it, or even after not rejecting it, the body does not get absorbed with it. So, nanomaterials would eventually work in making it something where the body would use the tissues, again use the proteins to make our devices with those. So, then it would be the body would take it as a, it is kind of related a little bit to the stem cell research, but again it is not, stem cell is you are making growing it, but here we are making artificially things which would be behaving the same way as what the cells or other things grow. So, that is the goal. So, the body will not be rejecting it. There are again to give you idea, we already have something like that which not people do not know it as a nano device, is whenever you have a surgery you use a string to kind of sew the thing back, but that gets absorbed into the body, you do not have to cut the stitch. So, that is what our future devices also should be like that, the body should be able to absorb that. So, again use of nano devices to study biological and mimicking biological processes with nano devices. This is also nanobiotechnology. You know how, what makes a lizard stick to the wall? That is what people used to think, yes, suction pads, but for to make a suction pad active, the wall has to be absolutely smooth, otherwise there would be leaks. You know, if you put suction pads on your fingers and if you try to put it on a wall which is rough, the suction pads are not going to. So, they actually use suction pads, that is right, but the suction pads are in the form of capillaries. So, they are in nano nature. So, they have a nano suction pad. I would show you a picture of what is the paw of a lizard. We do not call it lizard in the US and the other place, they call it by a name gecko, which kind of covers all types of lizard. So, that is the purpose. And why are those being used right now? There are gloves which right now are available in the military, it is not available by the common people, where you can be a Spider-Man. Okay. So, you can climb up using the same idea of how a gecko does it. Okay. So, in
tapes are also there, right? Gecko tapes are also there for hanging these heavy materials.
yes,
Somebody has commercialized this kind of a thing.
that's right. So, yes, there are tapes, the materials, again we are trying to mimic the biological processes. Other place where biological process has been used, mimicked, drone. Have you seen drones? They are this small, they fly in taking pictures or doing. How do they move that fast? People have been mimicking how flies, insects fly. So, insects, the way the insects fly is they flap their insecting wings lot quicker, number of times, lot faster, and the drones actually do the exact same thing. So, that is why they are actually mimicking the fly, and that is also the part of biotechnology. Okay. So, you would make things do the same things as what an insect does. Where does nanotechnology lead to? We try to get what we call, the purpose is to make a nano factory. We already have a nano factory, and that is a cell. Again we do not have no control of. So, the purpose of this is trying to make our devices do what the cell does. So, what does the cell does? It consumes simple substrates. Okay. So, most of the substrates, most things is they use is water soluble substrates. Then it operates, what is the operating temperature of a cell? 37 degrees, that is our body temperature. Any factory works at 37 degree? No, they work at high temperatures. Because of the high temperatures, the cause of all the other problems come in. We use solvents which are organic solvents which we have to dispose of, we would try to do it as water, if we can use water as a solvent. And the most important thing of the cell is it has a programmed recycling and disposal. Every cell is programmed that it would last this long, after that it dies, but what happened to the dead cell? There are organisms inside the cell which absorbs them, it recycles and comes back out. So, it is the most environmental friendly organism. So, if we can mimic this process and make it as our with, again the dimension of that is 100 micrometers, you can make it smaller, but the individual parts are in nanometer range. So, if you can get those, you would be. So, that is what is biotechnology is up to. This is on the left side is the size of the natural things, and this is our artificially created things. We have put the slide pictures in number of ways, but just to show a correlation in what we have been able to do it artificially and what is there naturally. Nanobiotechnology is supposed to link them together. And this is, if one of the main problems of nano devices right now, these devices we can have all made. You see, we have made electrodes with nanotubes. These are electrodes and these are the nanotubes. If you can see, these are the crosses of nanotubes. To make these, it is very expensive, time consuming process. But if we can mimic what is available in nature and use it to do that, then we would be able to make, as I said in the previous slide, what main problem of our nanotechnology was nano engineering. We can't make our nano things repeat and work as many times. In the nature these things are working forever. So if we can get those things together, so that is the purpose of nanotechnology. So again the scales of live bacterial virus, nucleus, there are I know a person in actually he works very close to my place, where they have found a particular a medicine which they call it which takes care of bird flu and the all type of viral infections related to that. How does it work? They put a nanoparticle, biological nanoparticle, and coat every bacteria with that. So the effect is the bacteria becomes the virus becomes. The virus, as you know, I'll tell you later, is virus is actually not living, means there's a difference between virus and bacteria. Bacteria you can kill, viruses you cannot kill. The reason you cannot kill viruses are not living beings, okay. They can reproduce, they need a host, virus needs a host, they go in over there and then they reproduce, and that is why if we take antibiotics when we have viral infection, it does not work, because antibiotics are penicillin which only works for bacteria, and if you take that when you have viral infection, you are basically putting your body's immune system under stress, okay. And that is why right now people are not trying to treat people with antibiotics, because if you put the immune system under stress, lot of other problems might crop up, and one of them is cancer, which is putting our immune system under stress, okay. So how do we stop a viral infection in that case? Our normal way is viral infection, you time it out, you have it and then few days and then it's gone. But for bird flu and the other, especially that infection stays longer, and the thing is it goes if it goes to infants, kids or elderly people, it may be fatal. So the way they do is they coat the virus with the nanoparticles. So once the virus is coated, they can go to the host, but they cannot reproduce, they cannot produce larger. So that is where nano particles are being used, and there are other materials for that or other. So this is the nano micro collaboration. It's just a cartoon to show that the microbiologists still don't know how small the nano is, but we would be okay. So let's a very quick knowledge of biology. There are I write it biology 101. So we would talk more when we talk about the other parts, but right now there are, how many of this class haven't seen, otherwise I'll jump next, haven't seen something like this, which everybody else have a biology background on this? Okay, so I will so there are two types of cell, primarily prokaryotic, and these are the advanced cells, which the main thing that you say is the difference is this has both DNA and RNA and it has a nucleus. These are our body cells are like this, these are kind of some bacteria cells. I will quickly go over these then. These are different parts of the cell and each part has its different functions. So since a lot of you have biology background, can I ask you to tell me what does this thing do? Sorry. So what does the Golgi complex do? Okay. So, it does protein modification, it actually, so how does this, so we would talk more about that when we when I give an introduction to that. So, what this does is it basically the different types of protein that it generates, it comes out of the Golgi complex, that is right. So, which is the garbage disposal organism which does for the cell? Okay, lysosome. So, everybody okay with this? Okay. So, we talked about the cells, we talked about different part, lysosome, packaging. Again, this is about DNA and hybridization. I do not think we have to different parts of, and I think it was already been mentioned in the previous class about what the DNA. Again, for non-biologists, I just wanted, because I was very confused when people use the word DNA, sometimes they use the word oligos. Do you know what is the difference between DNA and oligos?
Group 9 or 10, when they are grouped, they are known as oligos.
Yes. So, when you have this DNA, the long base pair, if you are having a shorter chain, then they are known as oligonucleotides. So, it is basically shorter DNA, okay, and they are known as. So, there are this is, we are trying to find nanotechnology in plants. For example, we are trying to see how bone, our human body has an amazing, if you look at the bone and if you look at the skin, they have two diametrically opposite properties. Bone is a ceramic. What are the properties of ceramic? It can take very high temperature, it can take wide structure, while on the other side of it is our skin, which is a polymer, which is a material which has exactly the opposite properties. Okay. So, our human, not only human body, any vertebrate body, you have the interface between bone. So, how does these bone cells and they work? That is what we are trying to replicate in nanotechnology. So, we look at what happening for the cell wall. There is, these are the middle lamella, the primary cell walls, and then you have the plasma membrane, and people are trying to, the main purpose of this is when you have artificial bones. The problem is how would you be able to make contact between artificial bones and the real bones. You would need to make a joint or contact with that, and the way currently it is done, it is not the best. I think they put, sometimes they put a steel screw and they kind of join two bones, or they put the steel, which with these it would be a better way if you can find out from the cellular level how things are kind of getting joined together. So, this is the molecule, this is talks about different type of amino acids, again the protein structure. I will just move over to, this is where I will come to the lizard or gecko. So, the nano bioforces, the forces are critical for the nano and biological interaction, and these forces are very much different from what you see in the macro scale. The surface forces dominate over volume, forces scale with size, but in biology, in nanomaterials, this is what we found out, but in biology these forces already are there. Giving an example, do you know about biofilms? Biofilms are when you have anybody who does not know about biofilm, do I have to give introduction? Okay. So, what is a biofilm? Biofilm is when you have biological organisms, they combine together. It could be biological organisms, it could be bacteria, it could be algae, it could be any of the other. What they do is when they see an unfriendly surrounding, For example, the same thing what happens to human beings also. You see a storm coming, a hurricane coming, what happens? Everybody leaves their houses and they go into a shelter, they kind of go there where they are protected. So, biofilms is the organisms do exactly the same thing. So, when they see an unfriendly surrounding, they group together and form a kind of a shell around it, and they time themselves out, and that is the reason why we need to have antibiotics or other thing for a certain number of time. Means even if you feel better by the second day, you still have to continue your antibiotic for 5 days or how many days that has been prescribed for. The reason is these organisms go into the biofilm form and then time themselves out, and as soon as the surroundings becomes more friendly, they can come out. So, they are not, they have not been killed, they are still alive over there. Oops. So, these biofilms, when algae forms it, this is a big problem for people in the shipping industry, because these biofilms can form anywhere. It does not depend. Normally when you form a film, we will want to look at a glue on which how the forces are kind of holding the film together. There are few places where biofilms are all there. One place where biofilm forms very common, anybody knows, in our human body? Yes, teeth. Okay. So, our teeth has a layer of biofilm formed on top of it, and that is one of the reason why as we get old you lose our teeth. As the biofilm gets more, then it kind of eats into the material and it loses. Anyway, how do we remove the biofilm? It is extremely difficult to remove the biofilm. If you want to remove the biofilm on your teeth, you have to use those high force water or something that goes in. So, why is the biofilm so strong? It is the biological forces which are holding it together. These biofilms are a big problem for the shipping industry. When a ship or a boat goes out into the ocean, when it comes back, it has a layer of biofilm formed on the surface. It's formed on the propeller, it's formed on it's more of a problem for submarines. And so, when a submarine goes once out, when it comes back in, next time it goes, it's consuming almost double the amount of fuel, because everything is being choked. I told you it's very difficult to join metals to metals, but these biological organisms are so strong that they are stuck to the metals and these biofilm are formed. So, that is, you can find out how strong the forces are, and it is very difficult to remove it. If the ship has to go to a dry dock and there has to be lot of scraping and all to remove that. So, the biological forces behave similarly. Surface forces, surface tension forces acting so strong that it is holding up on metal, which normally you would not be able to do, as strong as welding, even more strong than welding. Again, that is what we need, but it is very specific. You can't just take one organism, put it to the metal and let us say that this will be sticking it together. There are certain things which, that is what I am saying, is we do not know what particular chemical is kind of causing it that. So, that is what we need to investigate, and that is where nanotechnology comes in over there. Nanotechnology has tools by which we can find out what this thing is doing. I have in one of my own work, we have tried to find out how biofilm forms on different surfaces. We have made a smooth surface, we have made some patterns on the surface and tried to see how they attach themselves to the surface. So, we can actually study how individual things, and there have been more studies like that. So, this is what we talked about, the surface forces, and so the surface forces are, you see, gravity is proportional to the cube. The surface forces we work over here, they are proportional s squared. When you go more for biological size, these are the two forces which work together, capillary forces. I just talked about the lizard, gecko, what is holding it together. The weight of the lizard is quite a lot, but it is just the capillary forces which are holding it together. Capillary forces do amazing things. Capillary, they are the reason why the water goes up on top. Eucalyptus or any other trees, is air pressure cannot put the water up. We have so much problem on filling our tanks with water, but the trees have no issues at all. It is the capillary action which takes it. Even the sequoia plant which is there in California, which is like the trees are so big that you can cut the tree and make a highway under the tree. There is a place where you have a highway which goes under the tree. So, it is that big, but they also have water kind of reaching that with capillary action. So, this is the graph which shows the log of force and log of dimension. So, the nanoscale, when you go smaller, this is when we have the nanoscale forces, and the forces are in the order of what we call as line forces. So, this is the volume forces, these are the surface forces, and lot of these biological forces which come out as line forces. So, from chemistry we know there are different types of forces which are holding things together. We already know about the ionic forces which are attractive and repulsive forces, Coulomb forces holding together. Hydrogen bonding, that is the one why water has such a different property than the very close cousin to water. Which chemical is the one which should have had the same property as water if hydrogen bonding would not have been there? Yes, H2S. Okay. H2S, hydrogen sulfide. Sulfur is the next element in the periodic table. So, H2S and H2O should have been exactly the same property, but it is not. Why? H2O has hydrogen bonding, H2S does not have hydrogen bonding. That is why H2O is liquid, H2S is gas at room temperature, and lot of other things. So, hydrogen bonding, this is what our entire molecular biology depends on. That is what is holding the DNA together. It makes the DNA so strong, the hydrogen bonding, that we can still look at the fossils of dinosaurs, the DNA of the fossils from the dinosaur, and find out what their properties are. The DNA is so many billions of millions of years ago, the DNA still has survived. So, hydrogen bonding, it is something, and also we have what we call as van der Waals. If you look at normally which is the order of the strength of the forces, in the normal macroscopic scale this is the strongest force, then you would be seeing this, but when you go into the biological scale these forces behave just the opposite way. Actually ionic forces are the one which is not doing anything for the biological, it is the van der Waals forces that is holding the gecko together up there, capillary forces and all come in van der Waals, and the hydrogen bonding. This is what I showed. I would show you the picture of the adhesion mechanism of a gecko, or here they call or a lizard. You see this is the paw, and they have taken a scanning electron micrograph of the paw as you go higher, and they see you have these small capillaries, tubes over there, they go in smaller and smaller in dimension, and these are the ones which are actually the capillary forces are holding it together and in that small scale. There has been and they have been artificially, they have used multi-walled carbon nanotube. There are gloves where they have used nanotube, as I said, is a material which has a hole in there. So, you can use, again why they have used multi-wall, there are, I did not tell you when I talked about nanotube, there could be two different types, one is multi-wall and one is single wall. The picture I showed you over there is single wall is just having one wall around it, multi-wall is little impure, it will have number of walls around, but it is easier to make multi-wall, deal with multi-wall compared to single wall. So, that is why these guys have used multi-wall, it is nothing special property of multi-wall, but it is more easily available. So, that is why, and they have used that and they have ported it on the end of gloves, and that have made it the gloves the same kind of property as what these materials are. So, what are the properties of adhesives? Adhesives must connect surfaces through strong intimate interactions, adhesives must cure, and water is a big problem of adhesives. If you have a glue, especially that is the reason we do not have glue on the outside environment, always we use glue for where there is control, because where there is water it actually acts against. But in biological case water is the glue. So you are using, you might have seen if you have a plastic if you put a little bit of drops of water on the plastic, put it on the paper or another plastic and try to lift it up, you would be seeing they would be sticking with together. So that is why again if we can use water as adhesive over there, that will be our. So what are the adhesive forces in the biological model? Is it could be protein adhesion. So there are specific amino acids which react and or which they can have. Then there can be protein sugar adhesion, which is frequently used for binding cells to the external surfaces. This is where what happens for biofilms. That is why if you have lot of sweets, this you are actually increasing the chances of biofilm formation on your teeth, because you are making the biofilms those things to form with the sugar molecules. Then there are excreted polymers, polysaccharides, which also come from our saliva and other and adhere to surfaces one another. Now we have to replicate these some way. So so this was. So we have, there have been places where we have studied the proteins fold during the phot. There are two other big things that happen is in biology, or is there are two things which is known as hydrophobic, that is the things that when you put in water they do not dissolve in water, and hydrophilic. So when you have hydrophobic amino acid, there are some amino acids which are hydrophobic, it is intentionally made so that they does not get wet in water. So there are soluble proteins and membranes which get in over there, and then if it is hydrophilic, it is water soluble, then it is the hydrogen bonds which play in the role. We can have, if we have polymer adhesives, so we can use on polar surfaces. Polar surfaces means you have on one side you have one type of charge, on the other side you have another type of charge. So they combine with. So this is how the biofilms primarily form over here. So some of the microorganisms use acidic polysaccharides. So the marine bacteria, which we said, which are the one which is the problem with the ship, use carbohydrates which achieve a bond strength to up to 500,000 Newton per meter square, that is the strength. So that is why I said it is so difficult for it to, and it is done by these bacteria putting in these carbohydrate exopolymers. Actually these are known as extracellular polymeric organisms. So marine vertebrates also implement this, and again these say mussels, they adhere to surfaces. So this is algae invertebrates, they put in, again I do not know what this particular compound is, they use to getting bioadhesives. Again purpose of bio nanotechnology is if we can use this mechanisms and try to use it and making our quest for making better and better. Someday we might be using marine bacteria to glue our Boeing 787 to kind of the two composite materials, gluing it together, these might be. But the major problem of this is we have to keep it in an environment where the bacteria finds it friendly enough. If the bacteria does not find it friendly enough, there it adapts and it does not stay over there. So that is a big issue of finding out what makes the, so you have to keep the continuous supply of the polysaccharide or the food over there. So if you make a glue with the bacteria, maybe in a couple of days you have to inject it a little bit of food or something, and the bacteria will keep on. So next thing is bio nano devices, and we are putting in the bio nano devices in different sections. We call it nano biomems. Actually I think we are very close to our time limit. Okay, we are only just halfway through. So, I think this part we have already done, isn't it, in your previous lectures? Molecular transfer, lithography, atomic force. So, this part you must have already done. So, these are pressure sensors. These are there is a company which makes a glucose sensor where you do not have to prick yourself. They use optical properties to find out. So, it is like a laser beam which hits your finger and it gives you the sugar level, but these are not that, they are kind of for catheters and other places implantable. I think these I think some of which I think Professor Chakravarti also already talked to you about microchips, the glucose pump, he talked about that. Lab on a chip technologies. So, he talked about the microchannels, microfilters. So, if you take a drop of blood and how do you make it, one thing I think he told you about, I think this is a diagram which he used in his slide also, is how to control the flow. So, this is a lab on a chip, is how you mix it. The whole thing is put inside a chip, your whole pathological lab is being put inside a chip. These are disposable chips, I think he talked about it more. I will talk more about this DNA analysis later. So, this chip is for DNA analysis. We will talk more about this. Again, this is, I think he talked about, did he, I think he showed about these, I think he showed this slide also before. Did he or not? Okay, I'll talk about this more, but let me just go to the next. So, some of the materials, biological materials which we are trying to use to replicate. This is we know that this is a material which is used, bacteria rhodopsin. This is a light activated protein. So, there are materials which we can be using it for getting our materials working. So, this is one thing which we are trying to use. We are trying to get photosynthesis, we are trying to mimic photosynthesis. So, we could generate our, what is the main difference between photosynthesis and the way we generate our energy, any form of chemical energy? The main difference is, did Professor Das talked about this type of photosystem. So, here in Cornell University they have an artificial plant. There is a plant whose whole leaves are generated with artificial materials. Okay. The thing you would see, it is a very symmetric plant, unlike a plant which kind of goes a different size. So, they have been used to generate a bioelectronic, they are trying to simulate what happens in photosynthesis. The difference, the main problem with photosynthesis is the timing. You know, if you use a battery, a solar cell can act as something which can generate energy, but we can't control the amount of energy. When in photosynthesis, the adenosine triphosphate ATP, it is formed and then the energy is released. Energy is released very, very gradually in steps. That is the main problem which we are facing, is every time you try to restrict the energy to flow in steps, what happens is you lose the energy. Okay. So, you either have to extract the energy totally, then it is not working as a mimication of photosynthesis. So, this is the photosynthetic membrane. This talks more about how the photosynthesis works, you do not have to know more. And we talked about nanoparticle. How do we make nanoparticles? There are Do you know a natural way of making nanoparticles? In the nature nanoparticles are made. Yeah, no, this is bacteria I am talking about, but without bacteria.
Plot extract can be used for synthesis of nanoparticles.
Nanoparticles are made every time there is a volcanic eruption. Okay. So, whenever there is a volcano, how do you make nanoparticles? The main idea to make nanoparticles is you have to take a material, melt it down, and then you have to cool it very fast. Okay. And when it cools, you do not have to have a mechanism which kind of takes the liquid and kind of sprays it around, so that they do not cool and stick together. That type, wherever that situation is simulated, you have nanoparticles formed. So, a volcano is the only natural phenomena which produces nanoparticles up. Every time you start your motorbike or your scooter, you are producing nanoparticles. A car does not produce that many nanoparticles because they have a catalytic converter. Okay. So, those are the natural way of making nanoparticles, or the other you have to make it in the lab by doing the chemistry method. Here these are some of the bacteria which have been used to make. So, gold nanoparticles have been made by this bacteria, Bacillus. Silver nanoparticles made by this. How did people think about this? I will just give you a short. In Chile, in South America, there was a copper mine. In Chile is, as you know, is one of the largest exporters of copper. So, inside the copper mine the temperature was extremely hot, but when they looked at, they found there was a particular type of bacteria which was surviving inside that mine, where the temperature was so hot that everything was molten, and they found out that, I think that bacteria was, I did not put it over here, that bacteria actually eats the copper as its diet. So, it survives on copper, it takes the copper salt, and then once it is eaten, if you cut open the bacteria, inside the bacteria you find a pure copper nanoparticle being formed. So, that is from where people started working on finding out different ways of making nanoparticles. There is a way of making silver nanoparticles by adding something to, is it over here, actually lactobacillus, the bacteria which makes yogurt. If you add a particular type of silver salt to it, you can make nanoparticles inside the bacteria. The only way you have to get of the bacteria is after it is made, you have to kill the bacteria and extract the nanoparticle, means extract the bacterial cell and get the nanoparticles out from it. Okay, so magnetotactic bacteria. There are some bacteria which are magnetic field, they are influenced by magnetic field. So, I was on a PhD committee of a student who was using this magnetotactic bacteria for lithography, for fabrication of a circuit. They were trying to put this bacteria and small nanotubes connected to the bacteria, and they were applying the magnetic field. These bacteria gets activated by the magnetic field. So, if the bacteria, if they are in different directions, the bacteria you put in a magnetic field, they trace the magnetic field, and so you can make the bacteria actually work for you. They are actually working as laborers. They go in over there, they put the magnetic field. So, that was the PhD. The project was not complete because after the problem was after the bacteria does it, they have to kill the bacteria, otherwise it would bring the thing back again. If you switch the magnetic field off, then you do not know what the bacteria is going to do with it. So, your circuits would change. So, they were putting in a laser right at that point and they were killing, but they had issues with that. So, anyway, these are magnetotactic bacteria. There is a sewerage plant in Australia where they have put these bacteria, they put it into the waste, and then the waste is sieved into a big magnetic field. So, the bacteria eats the waste and it gets stuck to the magnetic field. So, when the water comes in, the dirty water gets stuck to the magnet, the other thing goes away. So, that is you purify your water by using this magneto. We are planning to work on nano composites. Okay, I think we are crossing our time. So, it is supposed to end at 1. Let me see how many we have. These are artificial. Let me see. Okay, we can do it maybe in our next class tomorrow. How many do we have? We are halfway through. This is the one which we said is making flat. Okay, we'll do it in our next class then. Okay. This is my research group, so we'll talk about that later. Okay, so I think I won't keep you longer over here. I'm not supposed to. So if you have any questions, can you ask me questions, or if you want to stay back and ask me questions in 1:1, I would be glad to address them. So in our since I see a majority of you know the biology part of it, my next presentation was, I think, an introduction to molecular biology. There was something. So how many of you have no clue about my molecular biology like me? I had. Okay, so it would be a repetition for some of you who had already have that, but we need to know that, because most of the problems which the nanotechnology is addressing is in the molecular level of. So we have to know what are the tools which are currently being used, because what nanotechnology would do, improve the measurement techniques. So you need to know what are the current measurement techniques, what is an test which biologists call the ELISA, ELISA, what does it do? You need to know what are some of the other tests and how nanotechnology can go and make those tests better. Better means faster and less amount of samples that you can take it. Okay, so questions? Yes.
How the AFM is involved in nanomedicine? You have given an example of atomic force microscopy.
Yes.
Since atomic force microscopy is basically involved in studying the structure of the molecule.
That's right.
So how it is involved in nanomedicine as such?
I will tell you the work which I did with my AFM. We were trying to find this is a bacteria which form a particular disease known as Lyme disease. Anyway, forget about what the disease is. This bacteria forms it forms biofilms. So Lyme disease is a disease which is basically got in ticks, small ticks. It's not common in this part of the world. Lyme disease is only common on the northern parts in North America or Europe. So what this bacteria does is they come in, they bite, and then the bacteria gets spread throughout the body. Initially you have the symptoms as a common cold. You sneeze, you have fever, 2 or 3 days back you feel fine. Then sometimes 10 years later suddenly you have symptoms of it. Most common symptom is you started getting symptoms like arthritis, like your joints start freezing up, even though it could be, that is how people initially detected it, that they were found in kids who were 12 years old. 12-year-old kids cannot move their hands, they are so much. I met a swimming champion. He used to be in the US Olympic team, but he couldn't swim anymore because his hands were getting arthritic symptoms. When they did a study, they found out that these bacteria goes and forms a biofilm in the joints, and that is why you have the symptoms. So my study was to find out how, with an AFM, how these bacteria biofilm forms. So what we did the study is we actually made the bacteria, cultured the bacteria, and try to see how it grows, and we actually found out that when the bacteria forms the biofilms, it's not a continuous. When a wall is being formed, as you know, it's not formed continuous, and when the bacteria form walls, initially there are holes, and then gradually as the biofilm gets, the holes initially are bigger in diameter and they gradually close, but they do not. So, that is what I say it can be used in nanomedicine, is these holes are available. If you can target those holes with the medication, then you might be able to kill the bacteria even if they are in the biofilm formation. It is like they are having a wall which is a porous wall. So, that is where we used AFM to find out. Also with the AFM, what we found out is how much they stick to the surface. So, how strong is the force of adhesion. So, that is the way we.
You are trying to study the interaction of the lead molecule from the drug versus the adhesion property of the cell surface of the microbe.
No, I am not using any drug. I am just using the microbe and seeing how it sticks to surface, and then how the biofilm grows. I am not showing it in this presentation, but I have pictures. We have actually kept the bacteria, and that is where we have to inject it some food every few days, and we kept the bacteria alive for, it is a slow moving, it is a slow growing bacteria. We kept it alive for almost 20 days, and in 20 days we kept on probing it and trying to find out how the biofilm grows, and we found out it still has holes in them. So, that is where we said using AFM for doing. The main problem is again capillary force acts against. Through those holes we tried to put something inside, but we could not. The reason is the surface tension forces, we had to use a pump. If we had a pump, then it could have gone in, but otherwise just the pressure was not enough to put something going in. So, if that is possible, then we could be able to break up biofilms. So, that was my work, but there are other people who have also worked with AFM in trying to see ex vivo how the nanoparticles or other things move in through the surface.
So, is it possible to separate out this bacterial eluted compounds in the biofilm? For example, it is forming a film and growing.
Yes.
And it will be synthesizing something as a extracellular
yes.
matrices or something. So that